ba 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 director. Man, what am I doing? Hello, and welcome again to another episode of Mr. Bell Physics. Today, we're going to be talking about light. Now, light is a very large topic within physics, so this video is going to be kind of a longer one, where we're going to be doing a few demonstrations here and there, as well as just kind of doing a general overview of what light is to begin with. So, feel free to kind of watch this one in multiple parts, because there's a lot to take in here. So, let's start off with the obvious question. What is light? Light, or electromagnetic radiation as it is formally called in physics, is a wave. So, what is a wave? A wave is a way that energy travels throughout a vacuum or through any medium. And it looks something like this, where we have kind of our standard kind of state of being here in the center. And things go up and down and up and down. Now, there are a few parts of this wave that we care about. For example, right up here, okay, this height, we call our amplitude. Okay, so this is called amplitude. Okay, this top part of the wave we call our crest. This bottom part of the wave we call our trough. Then from one part of a wave to the next part on the next wave, we call a wavelength. We know this whole thing is in motion with a velocity. And in theory, we could take a single point that the wave is going through and count how many times that wave is passing through every second. We call that our frequency. Now, this is a lot to take in by itself. I'm not going to act like it's not. For our purposes, when it comes to light specifically, we really only care about wavelength, frequency, and velocity. That's not to say that a wave crest and a wave trough and the amplitude of the wave don't matter, but they more are applied to things like sound waves and stuff like that, which we're not talking about right now. Now, a wave is something that's really well known within physics. So well known that it has an actual equation with it. So, if we come over here, if the camera wants to follow me, there we go. So right over to here. Perfect. The equation of any given wave like this for light is that our velocity is equal to our wavelength, represented by the Greek letter lambda, looks kind of weird, times our frequency. So, wavelength times frequency equals velocity. Now, for light specifically, the speed of light, or the velocity of light, is a constant value, no matter where you are in the universe. It is the absolute speed limit of the universe. We round this value to make our lives a little bit easier, but v is always going to be equal to 3 times 10 to the 8th meters per second. If you don't know scientific notation, you can rewrite that as 300 million meters per second, aka pretty fast. Okay, so light travels extremely fast, which makes sense. If I go off screen real quick, just to my light switch over here, and I turn off the lights, it gets dark almost immediately. Now, I have some string lights up around the room, so it may look a little bit weird. But when I turn the lights back on, the room is almost instantly filled with light. That's because light moves really fast. It's worth noting it does not travel instantaneously fast. Okay, there is an actual amount of time that is needed for light to fill a room. It's just an extremely short amount of time. We'll talk about how to calculate that time in a different video. For our purposes, we're just focused on the general properties of light. Now, with this equation here, velocity is equal to wavelength times frequency. Wavelength and frequency are related by the speed of light. That's 3 times 10 to the 8. That's 300 million. Okay? These two numbers multiplied together always have to equal that constant. Okay? They can never equal any other number. So because of that, when one of these numbers goes up, the other has to go down. It's kind of like a seesaw. So if I come back over here, so here, let's do this. There we go, camera. If we get rid of our wave diagram here for a second. We can imagine kind of a seesaw. Like this. With one side being wavelength and the other side being frequency, like that. Now, ultimately, this seesaw has to remain straight. Okay? This plank of wood or whatever the seesaw is made of has to remain straight. It can never, for example, do something like this, where it kind of just droops like that. Okay? It can never do that. The seesaw has to remain flat at all times. So, if either of these sides becomes bigger, so let's say wavelength becomes bigger, frequency has to also change to accommodate for that. So if this is normal, let's say wavelength gets bigger, we get something that looks like this, where one side went down and the other went up. And the opposite is also true. One side gets bigger, the other has to get smaller. We call this relationship being inversely proportional. One goes up, the other goes down. Okay, that is always, always, always going to be the case. We can show this off with something physical like a slinky, for example. So we're actually going to do a little bit of a new camera angle here. We're going to move all the way over here. Hi, you get to see my door now, and you get to see me a little more zoomed out. So make sure that the camera registers that. Perfect. What I have here is a slinky, and I've had the large one at that. Now, slinkies are a really great way to actually show off waves, especially mechanically. Okay. Unfortunately, with light, we can't really visualize waves very easily. Okay. They're impossible for us to actually see because they're very tiny and they're moving very, very quickly. However, with something like this, it's a lot easier for me to see a wave. So, I can create a mechanical wave just like this. Okay. Notice it's going to go back and forth and back and forth. This is because of something called wave interference. Waves can bounce off of things. Okay, this impacts how we actually see light. Okay, the reason why we see light is because light is either emitted by something, for example, one of these light bulbs here, or it is reflected by something. For example, blue light is reflected by this door. Okay? The mechanics of seeing color and all that is something that we'll tackle, again, in a different video as I get interrupted by our school bell. But yes, this is something that we'll focus on in a different video. For now, we're only focusing on the relationship between wavelength and frequency and the different types of light. So, wavelength and frequency. I can create something called a standing wave that kind of gives us a good visualization of a single wave. Okay? So, I'm going to start off by making one big standing wave here. Okay? Now, technically, this is actually half a wave because you only have the part going up, not the part also going down. But as you can see, it goes up and down at a rather uniform rate, and it has a clear arc to it. Now, if I increase the frequency, i.e. I increase how fast I'm making waves, they are still going back and forth at the same speed, okay, at that constant speed. But what we'll notice is that I can create more than one wave. Okay? So if I speed things up, okay, if I slow things down, I have one wave. But if I speed things up, I get two waves like this, where I get one half going up and down and the other half going up and down at a constant rate. Okay. Now, this looks a little bit crazy, and it is a little bit crazy. But the point being is that I increased frequency, but the wavelength had to get shorter to accommodate. Okay? I fit double the number of waves into the same amount of space because I doubled my frequency. Okay? By doubling the frequency, I halved my wavelength. Now, this is all well good and all, but what can I actually do with light? Okay? What's the point of it? And that's a good question. Okay? There's different types of light that do different things. In fact, there's 7 different types of light. So, if I stop this again, I'm going to list them out in the correct order. Now, light in general will always have either a high frequency or a low frequency, and vice versa for wavelengths, right? So, high frequency light has low wavelengths, very, very small. Big wavelength light has very low frequency. I'm going to write out the type of light, top to bottom, from longest wavelength to shortest wavelength. So, our shortest wavelength of light is called radio light. And this is the same kind of light that your car radio, for example, uses to transmit audio, right? So, light can carry information with it. So, radio waves are our lowest frequency, lowest energy light, and they have the longest wavelength. Okay, these wavelengths can go from a few meters to several kilometers. After radio waves, we have microwaves. This is the type of light that cooks your food in a microwave oven. Now, there are other uses for microwaves, but that's the one that we usually use in our everyday life. After microwaves, we have infrared waves. Infrared light is heat. Okay, so if you ever, put your hand above a fire and you feel the warmth of that fire, you're feeling infrared light being emitted onto your hand. Additionally, this is how most TV remotes work. Right, you usually have to point them directly at your TV box in order to make them work because they're transmitting a light signal directly to the box from the remote. So you need that straight path. After that, we have visible light. This is the type of light that you are the most familiar with. This is light that you can see, and is actually a very, very small part of the electromagnetic spectrum. Now, visible light can further be broken into the order of the colors, okay? That color order being red, orange, yellow, green, blue, indigo, violet, aka Roy G. Biv. This might be an acronym that you're familiar with. It might not be, right? Depending on what level of physics you're in, you may need to know that order. You may not need to know that order. Okay, this is usually something for our more advanced physics. So something that, for example, a high school senior would be taking. We'll talk about color theory and all that another time again, okay? Because colors do get pretty crazy. After visible light, we have ultraviolet light. And that kind of makes sense to come after visible because we end visible with violet. So ultraviolet is like the next step up. UV rays you're probably most familiar with from things like sunburns. Okay, the sun is a great emitter of UV rays. Okay, that's why you need to wear sunscreen to prevent skin cancer and sunburn. Because UV rays, at this point, we are now packing enough energy within this form of light to cause some serious harm to us. We also use ultraviolet waves to disinfect things usually, or as a black light to be able to see things. After ultraviolet, we have X-rays. You probably are familiar with X-rays either from the dentist's office or the doctor's office. This is the type of light that they use to take pictures of your bones. Okay? At this point, the actual wavelength of light is so small that it's able to go through you. Okay, it's able to go through your muscle, your tissues, right? All that. But it cannot quite go through your bones yet. So the light gets reflected by your bones, and that's what the camera ends up seeing. That's why we're able to take pictures of bones using X-rays. And then finally, we have gamma rays. Now, gamma rays are extremely short. At this point, these can absolutely ionize you. And there's a reason why gamma rays are oftentimes in science fiction used to describe dangerous forms of light. These are very high energy. Okay. Now, as I go down the list here, wavelength goes down. However, frequency goes up. So as I go down, wavelength goes down, frequency goes up, and energy also goes up. Energy and frequency go hand in hand. The way that you can think about it is that each light wave, individual light wave, has a small amount of energy that it's carrying. If I want to deliver more energy to a certain place, I need to increase the frequency of my light to deliver more energy. I need to deliver more light, right? If I can increase the number of individual waves, I can increase the amount of energy. So that's how this works. Now, this is all cool and everything, but what practical uses does that actually have for me? And furthermore, how can I do some calculations with it? So, in this next part here, okay, we're going to try something new here. I'm going to try to do an actual cut in my video, okay? We're going to look at a few different wavelengths of light, and then we're going to talk about how to do that calculation. So, stay with me here. Okay, so now that we're over here, I can show off a few different forms of visible light and their differences. Now, with regular light, what we've learned so far is that different wavelengths of light have different properties. Okay? Mainly, those 7 different types of light. So we have light that is very harmless to us, like radio or microwave light, and we have light that's very harmful to us, like X-ray and gamma rays, with the only difference being their wavelength and therefore their frequency, because those two things are always going to be related to each other. These differences can also be seen in the form of visible light, although it is a much smaller difference. So in order to show this off, I'm going to play with some lasers. Now, if you don't know what a laser is, it's essentially a very highly concentrated beam of light. And I can show that off using a laser and a spray bottle. So I have a green laser here, so I'm just going to point it over there. And right now you can't really see it. But what I could do is I could use this spray bottle because I spray a whole bunch of water to actually visualize that light. Now, we'll talk about the exact why this is able to happen another time. For us right now, it's not necessarily important. We just need to acknowledge that light exists. Now, this laser in particular, all lasers have to have their wavelength actually posted on them. And this wavelength has a wavelength of 532 nanometers. Okay, 1 nanometer, by the way, is 1 billionth of a meter. So divide 1 by 1 billion, and that's the ballpark that we're talking about here. So scientific notation will come in handy quite a bit in this unit, especially as we do our math. But right now, we just want to observe the difference in color. So I'm going to use this whiteboard in the back of my classroom to show this off. So 532 nanometers looks like this. Okay, should look like a just bright green dot right now. So 532 is solidly in the green range of the visible light spectrum, which is one small part of the electromagnetic spectrum. Now, using our acronym ROY-G-BIV, green is right in the middle, that G. Okay, red, orange, and yellow are all before it. Blue, indigo, violet are all after it. Now, what I'm going to do now is I'm going to take a laser with a different wavelength. Okay, if I try to actually read the wavelength, I need to go over into the light and actually to be able to read this. This laser has a wavelength of 650 nanometers. So 650 nanometers is going to be on the longer end of things. Now, if we think about this, as wavelength increased, we got closer to violet. Okay? Or no, as wavelength decreased, we got closer to violet. As frequency increased, we got closer to violet. So as our wavelengths got shorter and shorter and shorter and shorter, we went through ROYGBIV, okay, ROYGBIV. So we have a wavelength that is now longer than green. So in theory, this should give us something that is before G, so red, orange, or yellow. Let's see what we got. We got a little red dot. Okay. Now it may be kind of difficult to see on camera, so I'm trying to move it around to make it a little bit easier to notice. But this makes sense. Okay, a longer wavelength gives us more red light. Okay, red is all the way at the beginning of the visible light spectrum, where the wavelengths are the longest. Green is solidly right in the middle. Again, the difference is 100 nanometers, so 100 billionths of a meter. Finally, I have a 405 nanometer laser here. Now, 405 is a shorter wavelength than green. So in theory, we should be somewhere in the blue, indigo, or violet range. So if I shine this at my whiteboard, I should notice a violet dot. So we have gone all the way into violet. Okay? It's worth mentioning, as I increased the frequency by decreasing my wavelength, so as I went from red to green to violet, I not only decreased wavelength, which also increased frequency, I also increased energy. So violet light carries more energy with it. Okay, so looking at it would be a little bit more painful. But the point being in all this is that as we change our wavelength of light, we get different results over here. So what we're going to do now is we're going to go back over there to the whiteboard to do a mathematical example problem to actually see how these things relate to each other. So, diddly-doo, 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 and we're back. So, at this point, this is getting into pretty heavy physics at this point. So if you are in just a non-physics course and are just learning the basic properties of light, you're done at this point. But if you are in a physics course and are doing a little bit more than that, this is a little bit more, right? Being able to actually do these calculations out. So you are going to need a calculator for this. You're going to need one that can do scientific notation specifically. The reason why you need one that can do scientific notation is because these numbers are going to get really, really big or really, really small. So, what we have here is the speed of light equation, okay, for our wave. Velocity is equal to wavelength times frequency. We also know for a fact velocity will always equal 3 times 10 to the 8th meters per second, okay, or 300 million. We're going to do 2 examples here, okay? And I accidentally did a symbol that makes it start following me again. So, bring it back over here and stop. There we go. We're going to do 2 examples here, okay? One for red light, one for violet light. So, for red light, our wavelength, okay, so you gotta do, actually, no, we can even do this using a red and purple marker. Okay? We can color code this. Okay? How wonderful is technology, really? Okay? So, our red wavelength was 650 nanometers. Okay, so 650 nanometers. As you can probably tell, we're going to have to do a unit conversion here to make this all work, and that's okay. Okay, that's not anything to be scared of. For violet, our wavelength was 402 nanometers. So, we're going to calculate the frequency of each light to see how they're different, okay? So remember, this is how physically long the waves are, okay? So if I take a marker here and draw this out, what these numbers tell me is if I were to draw my wave like this, the distance from this point to this point is lambda. So for red light, this distance is 650 nanometers. For violet light, this distance is 402 nanometers. It gets smaller. It doesn't get smaller by a lot. at least not from our perspective. But for light, this is enough of a difference to really change some stuff. So let's do these calculations out to see how they come out differently. So let's start off with red. Okay. Now, 650 nanometers needs to be converted. So let's start off with doing that conversion. So I'm actually going to bring you guys over here. There we go. To do this conversion. So right about there. Perfect. So our given information in this case is 650 nanometers. So that is what I'm going to start with. Okay. 650 nanometers. And with any unit conversion, I know it's been a while since we did them, but with any unit conversion, we're going to start off by putting that over 1. This doesn't change anything about the math. Okay, 650 nanometers divided by 1 is still 650 nanometers. But this will be useful for us for formatting things later. Okay. Now, I'm going to multiply this by a conversion factor or another fraction. The unit that I want to get rid of will go on the opposite side of where it is now. So in this case, I want to get rid of nanometers. I want that to just be in meters. Nanometers is up top right now. I needed to go on bottom down here. So nanometers goes on bottom, and I want to get to meters, so that goes on top. Now, there is a direct conversion between nanometers and meters. Okay, using our metric prefixes, we can figure that out. Nano is the metric prefix for 1 billion of, or 1 billion per, rather. Okay, so for every 1 meter, there are 1 billion nanometers. So I'm going to write that shorthand as 10 to the power of 9. But this really is just 1 billion. Okay, same exact thing here. Okay, doesn't matter which way you write it. Okay, you can write it as 10 to the 9 or 1 billion. I like using 10 to the 9 because it makes less effort. Quite frankly, it's easier. Okay, at this point, I'm left in meters, so I know I'm done. I can cancel out my nanometers. And I just have to simplify this equation now. So 650 times 1 is 650. So that just goes right there. Divided by a billion, 10 to the 9. This is the only math I actually have to do to solve this. So doing that out in my calculator, 650 divided by 10 to the 9th power comes out to be 6.5 times 10 to the negative 7. And don't forget to include a unit of meters. Okay, so that's what I'm left with doing my unit conversion for red light. Let's do it for violet light now. Okay, so we're going to kind of go back and forth here a little bit. Our conversion is going to look almost identical, except instead of 650, we use 402. So going back over here, towards the bottom here, 402 nanometers divided by 1 times our conversion factor, nanometers on bottom, meters on top, 1 meter for every 1 billion nanometers. We get 402 divided by 10 to the 9. Do that out in your calculator. And you get 4.02 times 10 to the 7. To negative 7, that is. So those are our actual wavelengths that we'll be using for these problems. Now that we have those, I can bring you guys back over here. If it wants to. Come on. There we go. Hi. So I can bring you guys right over to, let's go here. Perfect. Okay. So I have my converted wavelengths now. I have my velocity up here. Okay. Probably should have written it in black, but I'll box it in black. That way we can always just access it. And I have my equation up here. So now I can plug in and solve. So let's start off with red light. So my velocity is 3 times 10 to the 8th equals my wavelength, 6.5 times 10 to the negative 7. times frequency, which I don't know yet. Now, what we're about to do is divide a really big number by a really small number. This should give us a ludicrously big number. These are probably the biggest numbers that we'll be working with all year in physics. So let's do that math out. Okay. In order to get f by itself, f is being multiplied by the 6.5 times 10 to the negative 7. So to undo that, we do the opposite of multiplication, which is division. So divide both sides by 6.5 times 10 to the negative 7. Divide by 6.5 times 10 to the negative 7. These cancel out. Frequency becomes, doing this out in my calculator, I am getting 4.62 times 10 to the 14. Now, for frequency, we have a specific unit that we use for this, okay? Because this is really the number of waves per second that we just calculated. Now, a old dead scientist, whose last name was Hertz, discovered this. And so, in memoriam of him, the unit that we use to describe frequency is Hertz. So, our final answer for red light is our frequency is 4.62 times 10 to the 14 Hertz. What does that number mean? Okay, it's a good question. So, if we remember for a fact that 10 to the 9 is a billion, therefore 10 to the 12 is a trillion, we're at 10 to the 14. So we are dealing with 462 trillion waves per second. It's a big number. Okay, so big that we can't really wrap our head around it. But for light, this is kind of what we have to deal with sometimes. Now, again, this is longer wavelength, lower frequency. When we do the exact same math out with the 4.02 times 10 to the negative 7 down here, we should end up getting an even bigger number. Let's see what we got. So, to solve for the frequency of violet light, we do the exact same thing. We start off with our formula. Okay, start off with the speed of light, 3 times 10 to the 8. Equals our wavelength, 4.02 times 10 to the negative 7. Times f, our frequency. The process is the exact same. We want to get f by itself. F is being multiplied by our wavelength right now. So to undo multiplication, we do division. And anything we do to one side, we must do to the other. So divide both sides by 4.02 times 10 to the negative 7. And when we do that out in our calculator, we're still dividing that one really big number by a really small number. But the number has gotten even smaller now. Okay? Instead of 6.5, it's 4.02. So let's see just how much bigger our final answer actually comes out to be. Our final answer in this case is 7.46 times 10 to the 14, and then don't forget your unit of hertz. So for red light, our frequency was about 462 trillion. For violet light, it's 746 trillion. Okay, almost double. Okay, almost twice as much. With light, it's very difficult to wrap your head around these numbers sometimes. Okay, you just kind of have to blindly trust your calculator, which is ironic, seeing as you're blind in that sense, and we're talking about light. But it's the truth. So this is how you would calculate the frequency of light, and this is how we know that different lights have different frequencies as well as different wavelengths. Remember, we have multiple different types of light depending on those wavelengths and frequencies. So hopefully this was very useful to you in terms of getting a better understanding of how light in general works. So as per usual, I hope that this video was helpful for you. Make sure to absolutely smash that like button, right, to let me know that you liked the video. Make sure to subscribe and hit that little bell for notifications for every single time that I upload. And as per usual, I will see you all in the next video.